So the last topic of chapter number 5 is the discussion of circuits that can change the phase at the output with respect to the input signal. There are two types of circuits that we are going to discuss under this topic. One is the phase lag circuit, in which the output phase is going to be lagging the input phase, and the other is phase lead circuit, the circuits that produce output phase, which is leading the input phase. So we are going to start with the discussion of all pass phase lag circuit. The term all pass means that the magnitude of the output is not going to change. It is going to be the same as the input magnitude. However, the only thing that is going to change at the output is going to be the phase of the output signal, which will be lagging the phase of the input signal. So this is the circuit in figure 5.12 that shows you a phase lag circuit. It's an all pass phase lag circuit. We can go ahead and solve it to see if the magnitude of the input and output, they're the same, and if the output phase is lagging the input phase. And the way we solve it is, first we find out what is the voltage at the non-inverting input, which will also be equal to the voltage at the inverting input of the operational amplifier. So voltage at the non-inverting input can easily be found out by applying voltage division at the non-inverting input. As you can see by this arrow, I applied voltage division across the capacitor, and the voltage across the capacitor will simply be, using voltage division, XC over R, XC over R plus XC times the input voltage, which input voltage is across R, the combination of R and C. So the term is given right here. The voltage at V positive is XC over R plus XC times V input. And of course, XC is 1 over j omega C. So you can go ahead and plug that in, 1 over j omega C over R plus 1 over j omega C V input, which will give you 1 over R plus 1 over 1 plus j omega RC. So that is the voltage at the non-inverting input. And again, the same voltage is going to appear at the inverting input as well. Now we can apply KCL at the inverting input with I1 equals to IF. I1, of course, with Ohm's law, it's going to be V input minus V positive over R1. And this is going to be equal to IF, which is V positive minus V output over R1. Observe that in the feedback loop and in the input, the resistor that is connected to the inverting terminal, they have the same value, R1, R1. So when you equate them, they're going to be cancelled out, and you're going to have V input minus V positive is equal to V positive minus V output, which will give you, if we write it down in terms of V output, which will give you V output is equal to 2V positive minus V input. V output equals 2V positive minus V input. And this equation, it is on the next slide. V positive we found out first, then we applied KCL at the inverting terminal, and we get V output equals 2V positive. Of course, all of these are in phasor quantities, so function of j omega minus V input. V positive, we found out it is 1 over 1 plus j omega RC V input. So we go ahead and plug that in. 2 times 1, of course, 2 over 1 plus j omega RC V input j omega minus V input j omega. So when we simplify this, it is going to give us 1 minus j omega RC in the numerator divided by 1 plus j omega RC, which is the denominator of this term, times V input. And the ratio between the output and the input, which is the gain, or we call it transfer function. Transfer function is equal to 1 minus j omega RC over 1 plus j omega RC. When we calculate the magnitude response of this from this equation, complex number magnitude response, if complex number is given in fractional form, is the magnitude of the numerator divided by magnitude of the denominator. So magnitude of the numerator is a square plus b square, square root of that, so square root of a square 1 plus b square negative omega RC square, and the same goes for the denominator. So the term in the numerator and denominator, they're the same. Therefore, the magnitude of the transfer function is 1, which means that the output voltage at all frequencies, magnitude, that is, output voltage magnitude at all frequencies, should be equal to the magnitude of input voltage at all frequencies. As we said, it's an all-pass filter. Now, when we look at the phase from this expression, h of j omega, remember the phase of a complex number given in the fractional form is the phase of the numerator minus phase of the denominator. And phase of a complex number is tangent inverse of the imaginary quantity divided by the real quantity. Imaginary part of the number, complex number, divided by real part of the complex number. So when we calculate phase of this, it's going to be tangent inverse of negative omega RC divided by 1, or in general, tangent inverse of negative omega RC minus tangent inverse of omega RC over 1, or tangent inverse of omega RC, which you can see right over here. Tangent inverse of arctan of negative omega RC minus arctan of omega RC. Tangent inverse of negative omega RC is the same as negative arctan of omega RC. It's in the fourth quadrant in the complex plane. So the fourth quadrant angles are taken as negative angles between 0 and negative 90. So it's the same thing as negative of arctan omega RC, which is arctan omega RC is going to give you a phase in the first quadrant between 0 and 90, and then there's a negative sign outside. So negative arctan omega RC minus arctan omega RC is going to give you negative 2 times arctan omega RC. And this is a phase of your h of j omega, which is the transfer function between the output and the input. Now, the output phase, so remember the output is equal to h times the input. I'm not showing j omega, but all of these are function of j omega. So the magnitude of output is equal to magnitude of h times magnitude of input. Remember, magnitude of h is 1, so output magnitude is equal to input magnitude. And phase of output is phase of h. And when two complex numbers are multiplying and you're calculating phase of the corresponding quantity, then the phases add together, plus phase of the input voltage. Now, phase of h is negative 2 tangent inverse of omega RC. That will be added into the phase of the input signal. So negative 2 tangent inverse omega RC. When omega is 0, tangent inverse of 0 is 0. So at 0 frequency or at DC, the phase of h is going to be 0, as you can see over here. When omega is 1 over RC, which is the cutoff frequency, then that's going to become 1 over RC times RC. And tangent inverse of 1 is 45 degrees. 45 degrees times 2 is 90 and negative 90. So at the frequency 1 over 2 by RC, or at omega 1 over RC, the phase is negative 90 degrees. And when omega is going to become extremely large, tangent of extremely large number, tangent inverse of extremely large number correspond to 90 degrees, because as the value of sine is increasing from 0 to 1, you are moving from 0 degrees to 90 degrees for sine, and cosine, when you move from 0 degrees to 90, cosine is decreasing from 1 to 0. So the ratio between sine and cosine, which is tangent, as it hits 90 degrees, sine is 1, cosine is 0. So if you take the limit at 90 degrees, the tangent value is going to be infinite. At 90, it does not exist. But as you're going close to 90 degrees, it becomes very large value, almost infinity. So anytime you're taking tangent inverse of a very large number, that corresponds to 90 degrees. So omega tends to infinity means tangent inverse of infinity is going to be 90 degrees times -2, which will be -180 degrees. And that's what you see in figure 5.13, that as omega becomes very large, then the angle becomes -180 degrees, and that's going to be the final angle. So this means that the output phase is equal to the input phase plus the phase of the transfer function, and the phase of the transfer function is changing between 0 and -180, which shows that the output will always be lagging the input as far as phase is concerned between 0 degrees and -180 degrees. Hence, the name phase lag circuit. And of course, we already discussed that the magnitude is 1 for all frequencies, as you can see from figure A, 5.13 figure A, that the magnitude is 1 for all frequency, thus all pass. So this is all pass phase lag circuit. Similar to the phase lag circuit, we have phase lead circuit, again all pass. So the magnitude again is going to be 1 of the transfer function, which means the output magnitude shall be equal to the input magnitude. And it is going to be phase lead circuit. That means your output phase is going to be leading the input phase. The circuit is very similar. The only difference is we replaced C by R and R by C. So we switched C and R connected to your non-inverting terminal. And we do the same thing. We apply voltage division at the non-inverting terminal. We are going to get the voltage across resistance as V positive, and that is going to be V input times R divided by R plus XC, which is given right over here. And this voltage will be the same as V negative. So once again, we are going to apply KCL at the inverting input. I1 is equal to IF. Since again resistors are the same, therefore our equation is going to be the same, which is V input minus V negative is equal to V negative minus V output, which will give us the same expression, that is V output is equal to 2V negative, and V negative, V positive are the same, so 2V positive minus V input. In this case, V positive, of course, is 2 times R over R plus XC times V input minus V input. Therefore, the output is going to be 2 times R plus XC times V input is going to be, the 2R will be cancelled out, so it's going to be -2 XC over R plus XC times V input. Sorry, we have 2R, so it's going to be R minus XC. Fix this. So 2R minus R is going to be 1R, so it's going to be R minus XC. And once again, X of C is 1 over j omega C and 1 over j omega C, which will give us V out to be -1 plus j omega RC over 1 plus j omega RC. So that is going to be the expression for V output in terms of V input. -1 plus j omega RC divided by 1 plus j omega RC. And the transfer function, which is V out over V in, will simply be -1 plus j omega RC over 1 plus j omega RC. Now, anytime again you are dealing with, and so the magnitude of the transfer function is again the magnitude of the numerator, which is the square root of -1 square, which will be 1, plus omega RC square, divided by magnitude of the denominator, which will be 1 square, which is 1, plus omega RC square. So again, magnitude in the numerator, magnitude of the numerator and denominator will be the same. Therefore, the magnitude of H is going to be 1. As far as phase is concerned, observe that the numerator, the number, it lies in the second quadrant of the complex plane. So your complex plane, you have on the x-axis real number, on the negative x-axis negative real number, on the y-axis you have imaginary number j omega, and negative imaginary number negative j omega. So the numerator is -1 plus j omega RC. -1 is going to be here. And any value of j omega RC is going to be on the positive imaginary plane. So let's say you have this value. And this value is going to be in the second quadrant. So all of the values in the numerator are going to be in the second quadrant. That means the phase is going to be between 90 degrees and 180 degrees for the numerator. And the phase of the denominator will be between 0 and 90 because that's going to be in the first quadrant. So let me go to the next slide. Again, derivation is here, and this is h of j omega. So phase response. H of j omega is arctan of omega RC divided by -1, which is in the second quadrant, minus arctan of omega RC over 1. Now this, as I said, it's in the second quadrant. That means the phase is between 90 degrees and 180 degrees. So this can be written as 180 degrees minus arctan of omega RC. Why? Because arctan of omega RC is in the first quadrant. Let's say this angle. Let's say this is 30 degrees. But this is not your point. The point is right here. So this point is, let's say, 1 and then J2. But your point is -1 and J2. So your angle is not 30 degrees. Your angle is this. This is 30 degrees right here. So your angle is 150 degrees. So how are you going to get 150 degrees? You're going to take 180 degrees and subtract this angle, 30 degrees, which is arctan of omega RC. And that's why you see 180 degrees minus arctan of omega RC, which is your required angle. In this case, let's say it is 150 degrees. And then negative arctan of omega RC, which is the phase of the denominator. So your total phase is 180 minus 2 times arctan of omega RC. Once again, when omega is 0, then your phase is 180 degrees. That means phase of the output, which is equal to phase of H plus phase of the input. When omega is 0, the output is going to be leading the input by 180 degrees. When omega is infinity, then arctan of infinity is going to be 90 degrees times 2, 180. 180 minus 180 is 0. So when omega is infinity, very large frequency, output and input phase are going to be the same. And when omega is going to become 1 over RC, which is the break frequency or cutoff frequency, then arctan of 1 is going to be 45 times 290. So the output will be leading the input by 90 degrees at that time. So in any case, when omega is changing from 0 to infinity, the output will be leading the input between 180 degrees by 180 degrees up to 0 degrees. That is same phase. And this is a graph to show that the phase of your h of j omega, what we are calling theta omega, is changing between 180 degrees at omega is equal to 0 to 0 degrees at omega when omega becomes very large. Therefore, output phase will be leading the input phase by between 180 and 0 degrees. So that's an all-pass phase lead circuit. Design an all-pass phase lead circuit with a phase shift of 112 degrees at 1.5 kilohertz. So it's a phase lead circuit, which is this circuit right here. And we have to design such that the phase shift at 112 degrees is 1.5 kilohertz. So the phase of H of j omega is 112 degrees. So let's say the input is given, V input is 5 cosine 1.5 kilohertz, means the frequency is 3000 pi radian t. So that's the signal in time domain with frequency 1.5 kilohertz or 1500 hertz. 1500 hertz means omega will be 2 times 2 pi f, so 3000 pi. So this is your omega. For this, we want the output to be 5 cosine 3000 pi t plus 112 degrees. That's what we want. So the phase difference between the input and output is 112 degrees, with the output leading the input by 112 degrees. That means the phase of the transfer function is 112 degrees. Phase of the transfer function is 180 degrees minus 2 times arctan of omega RC. 112 is H omega, 180 is here. So 180 minus 112 is 68. 68 degrees is 2 times arctan of omega RC. And arctan of omega RC is 34 degrees. Arctan of, we are using right here, 2 arctan of omega RC. 34 degrees. Which means omega RC is tangent of 34 degrees, which is, let me calculate it real quick. Tangent of 34 degrees is 0.6745. 0.6745, which means the product of R and C is 0.6745 over omega, which is 3000 pi. 3000 pi. So divided by 3000 pi, which gives us 71.56 exponent negative 6. 71.56 exponent negative 6. So we do not know R, we do not know C, of course. But you have to choose one of the values and calculate the other value. Generally, the recommendation is to choose the capacitor value, since there are limited values of the capacitor in your kit, basically, your electronic components kit. Choose a value that is common. Now, remember, resistor, there are many values available. And even if the value is not there, you can always create series combination or parallel combination of resistors to get to the value, closest value that you need. But capacitor, they have limited values, especially the one that we use in labs. So one of the common values of capacitor that we use is 10 nanofarad. So let's say C is 10 nanofarad, which implies R is going to be 71.56 over 10 nano. Let's see. Over 10 is 7.1. So 7.15 or 7.1 kilo. 7.1 kilo ohm. That value is not really, I believe, a standard value. Let's go ahead and check that. But I believe 5.1 kilo ohm is a standard value, and you can use that in series with two 1 kilo ohm resistor. Or if 5 kilo ohm is their standard value, then you can use a 2.1 kilo ohm in series. But anyways, you can make combinations of that to get to 7.1 if it is not a standard value. So this is a good set of value. Now remember, you're not supposed to use very large value of resistor because of noise, as we discussed, or very small value either, because again, they are affected by the noise. So in kilo ohms, they're fine. 7.1 kilo ohm is a good value, and it can be used in the circuit. As far as the other two R's are concerned, R1, R1, they're the same basically. You can choose any values. Let's say choose 1K or 10K for both of them, and that should work. So this is how you can design a phase lead circuit, and the same way you can design a phase lag circuit as well, because the process is not going to be the same. So this is phase lead, and the same way you can design a phase lag circuit. Don't assume this is a phase lag. It's a phase lead circuit.